2560 it takes us through a series of reactions that we'll just walk straight through. So the first step is Br2 in light. So that should be a radical bromination reaction. The light will break apart the Br2, making a bromine radical. The bromine radical can pull off any of these hydrogens, they're all the same. And then the other bromine radical, or the radical can react with bromine, is probably more accurate in order to form this type of product. Once we have the bromine installed, that bromine can react a ton of different ways. Using potassium tert butoxide, which is what happens between A and B, is a pretty clear indicator that we don't want to go through any sort of nucleophilic substitution. This is a really strong base, and it really is only used for eliminations. So we're going to pull off either this hydrogen or this hydrogen. Again, both of them giving us the same cyclohexene product, and that cyclohexene can then further react. So product B is a cyclohexene. We can react with NBS and CCl4. This is just a solvent, tetrachlorocarbon, or tetrachloride, carbon tetrachloride, and heat. This reaction allows us to generate radicals in bromine at really low concentrations, which allows us to keep the double bond and only react at the allylic position. The allylic position, again, would be the one right next to the double bond, but not on the double bond, so either here or here. Again, both of those products are identical, so we can end up with either version. When you use sodium hydroxide can be a nucleophile and go through a substitution reaction, or it can be a base. So we could either end up with a diene in this case, or we could end up with an alcohol. The concentrations and other conditions are actually really important here, and your textbook doesn't give you any of them, which is kind of confusing. The real hint comes from the fact that the next reaction is an oxidation, so we probably want the alcohol there. So if we have an alcohol here like this, we can oxidize. That oxidation will give us now an alpha-beta unsaturated alkene. The carbonyl, and then at the alpha and beta position, the alkene. The next set of reactions are a Gilman reaction. So the Gilman reaction installs just one of these carbons, and it always installs at the beta position. It never adds directly to the carbonyl. And so we end up having a product that looks like this. Now it also asks us to react this product F with product C after it's been reacted with the magnesium, or product G. So product G is going to have the Grignard reagent right here, magnesium bromide, and it's going to react with this carbonyl. The second step of that reaction is just an acidic workup to get rid of the alcohol. So we're going to have this add on to this position in H. It's a little bit difficult to draw. Hopefully you can still see this. So we'll end up with an OH here. We'll have a new bond between this carbon and the other ring, and this carbon will remain allylic to double bond. So we'll have a double bond 1 over. You could either have it up here or down here. It doesn't actually matter how that's drawn. The last step is Br2 in carbon tetrachloride, and because we're having a high concentration of Br2 here, we'll actually react this location instead of at the allylic position. We'll actually just go through a normal electrophilic addition. And so we'll end up with a product that has the same ring that we see over here, still have an alcohol, and then we'll have, instead of the alkene here, we'll have 2 bromines. These bromines are going to be trans to each other, but we'll have both versions, both enantiomers of that molecule. And because this is also chiral, we'll end up with a huge mix of products, which is why I didn't indicate any of the chirality on any of this.